Hello, welcome back. From today onwards, in few classes we are going to discuss the magnetic properties of solids. The magnetic behavior of solid can be classified into three groups. One is paramagnetism, diamagnetism and ferromagnetism. When a substance is placed in a magnetic field H, and then there will be some magnetization in the material. Okay, if M is the magnetization in the material, the magnetization M, which is the magnetic moment per magnetic moment, total magnetic moments per unit volume of the specimen. Okay, so this M is given by M is equal to chi times H, or M is proportional to the magnetic field H. Here chi is the magnetic susceptibility. We can say the material is diamagnetic, paramagnetic or ferromagnetic depending on the value of this chi. If chi is positive, it can be paramagnet or ferromagnet. Okay. If chi is negative, it will be diamagnetic. What is the meaning of chi? If chi is negative, this magnetization is opposite to the magnetic field. That means the material will have a tendency to move away from the magnetic field. Okay, so that is called a diamagnetic behavior. And if chi is positive, the magnetization is in the direction of the magnetizing field. So there will be a tendency of the material to move towards the magnetic field. Okay, so for a diamagnetic substance, the chi is small negative quantity for diamagnetic material, and for paramagnetic material chi is small but it is positive. Okay, and for ferromagnet also it is positive but it is large. Okay, so this is the susceptibility and magnetism. The diamagnetism produces negative susceptibility and is independent of temperature. So the diamagnetic susceptibility is independent of temperature. Okay, but the paramagnetism produces positive susceptibility, which is temperature dependent. Okay, so this is temperature independent here, temperature independent. Okay, but this paramagnetism, for paramagnetism, chi is small, positive, and temperature dependent. So in this chapter, we are going to discuss more about the paramagnetism and diamagnetism. Now, the magnetism of a free atom has three sources. It can be due to three sources. First one is the spin angular momentum of the electron, or spin motion of electrons in the atom. Okay, so there are three sources for magnetism. One is spin of electrons of the atom, or spin angular momentum of the electrons. The second contribution, or the second source is the orbital motion or orbital angular momentum of electrons of the atom. And the third source is the change in orbital moment or orbital angular momentum, uh, orbital magnetic moment due to applied magnetic field. Okay, and the first two sources are creating paramagnetism, whereas the third one causes diamagnetism. Let us consider the case of a hydrogen atom. 1s1 is the electronic configuration. So here the orbital angular momentum quantum number L is equal to 0 for s orbital. Okay. So if L is equal to 0, that means the orbital magnetic moment is 0. Then the magnetism is only due to the spin of the electron. Okay. So for this hydrogen atom, only magnetic moment is due to the spin, and there will be induced magnetic moment as well. But for helium atom in the ground state, that is 1s2 is the electronic configuration for helium. Okay. Then here the it is completely filled in the s orbital. Therefore the spin cancels. Spin of these electrons will cancel each other. Then spin magnetic moment is 0. Since this is in s orbital, the orbital angular momentum also 0. Okay, both s equal and l also 0. L is equal to 0, S also 0. So therefore, there will not be any magnetic paramagnetic contribution for the helium atom in the ground state. Therefore, only induced magnetic moment is there. That is the only for helium atom only diamagnetism exists. Okay, no paramagnetic contribution. And for all field shell, the spin and orbital momentum is 0. Therefore, the corresponding magnetic moment is also 0. Okay, so only diamagnetism exists for field shells. In this video, I'll be talking about diamagnetism, especially Langevin diamagnetism. Okay, the diamagnetic behavior can be explained with a reference to Lenz's law. We know the Lenz's law in electromagnetic induction. According to Lenz's law, when the flux through a current carrying loop is changed, an EMF is induced in the loop in such a way that this EMF opposes the change in flux itself. So an EMF is induced due to the change in flux. This EMF opposes the change in flux. This is exactly what happens in the diamagnetism. The diamagnetism is due to the external field, external applied magnetic field. This creates diamagnetism which opposes the this field. Okay. Now let us discuss the Langevin diamagnetism. Okay. Let us consider the influence of a magnetic field on the motion of an electron in an atom. So we can consider the electron which is revolving around the nucleus in the atom, and if B is the magnetic field which is along the z direction, so this field is passing through the nucleus. Okay, so this plane of motion, this plane of motion of electrons presses around the magnetic field. Okay, so this precession is called the Larmor precession. So the plane of motion of electron presses about this magnetic field when a magnetic field is applied in this direction, and the frequency of this precession called the Larmor frequency, uh, angular frequency, is given by uh, EB. E is the charge of electron and B is the magnetic field. EB divided by 2m. Okay, this is half the cyclotron frequency. So 1 by 2 times EB by m, which is the cyclotron frequency, and therefore the Larmor frequency omega L is equal to EB by 2m. Therefore, the Larmor precession of Z electrons. There are Z number of electrons in an atom, where Z is the atomic number. The electric current I is equal to charge into the number of revolutions per second. Okay, so the charge of Z electrons is minus Ze into the number of revolutions per second is, so this is angular frequency. Therefore the frequency is the number of revolutions per second, so which is given by omega divided by 2 pi, that is 1 by 2 pi times E into B divided by 2m. Therefore the magnetic moment of the current loop, we can write the magnetic moment of the current loop is given by mu is equal to the current in the loop I into a is the area of the loop. So we have studied this relation in our elementary classes. uh, the magnetic moment of a current carrying loop is given by the product of current and the area of the loop. We can write this is minus ZE times EB divided by 4 pi m into area of the loop is pi rho square. Here this plane of the loop presses about the magnetic field. This is the plane, this is the direction of the plane of the loop, and this plane this presses about the field with the frequency of this thing omega L is equal to EB by 2m. Then the magnetic moment due to this precession is I into A, which is given by this relation. Here the area of the loop is pi rho square. Here rho square is the mean square of the perpendicular distance of the electrons from the axis. Okay, perpendicular distance, which is given by mean x square plus mean y square. But the mean square distance r square is equal to mean x square plus mean y square plus mean z square. Okay, for a spherically symmetric electron distribution around the nucleus, then if the electrons are revolving around the nucleus in a spherically symmetric manner, okay, so therefore we can write mean x square is equal to mean y square is equal to mean z square is equal to uh, mean r square divided by 3. Okay, therefore rho square is equal to 2 divided by 3 x square plus y square, which is equal to r square by 3 plus r square by 3. So 2 times r square by 3, or 2/3 of mean square distance r square. Okay, here mean rho square is the distance of the electron, mean square distance of the electron towards the axis of the rotation, and mean r square is the mean square distance of the electron towards the nucleus. Okay, so this is related by, these two are related by the same. Therefore the magnetic moment mu is equal to minus Z E square divided by Z E square into B divided by 4m into rho square is equal to 2 by 3 mean r square. Okay, so this is the magnetic moment, and therefore the magnetic susceptibility chi is equal to m divided by h, or which is equal to, we know that magnetic field intensity B is equal to mu 0 times h. Okay, therefore this can be written as mu 0 m by m divided by B is the magnetic susceptibility. Okay, therefore we can write this is mu 0 times, if n is the number of atoms per unit volume, then we can write total magnetization M is equal to n into mu divided by B. Okay, so therefore this is equal to mu 0 into n into mu is nothing but minus ZE square B divided by 6m into mean R square divided by B. Okay, so these B get cancelled in both the numerator and denominator. Therefore, the diamagnetic susceptibility chi is equal to mu 0 n minus mu 0 n Z E square divided by 6m into mean of R square. Okay, if we know the mean square distance, then we will get the expression for the diamagnetic susceptibility. Okay, so this is the diamagnetic susceptibility or Langevin diamagnetism. Okay, or this is Langevin equation. Okay, when a magnetic field is applied on an atom, then the plane of motion of the electron around the nucleus presses about the magnetic field with a frequency called Larmor frequency. So the magnetic moment due to this revolution of electron around the nucleus is given by mu is equal to I into A, where I is the current and A is the area of the loop. So if we know the current and area of the loop, we'll get the magnetic moment. If there are n number of atoms per unit volume of the specimen, then the total magnetization m is equal to n times mu. Therefore, the total magnetic susceptibility chi is equal to m by h is equal to mu 0 n mu divided by b. So, if you substitute the value of mu, you will get the magnetic susceptibility chi is equal to minus mu 0 n z e square divided by 6m into R square. Okay, mean R square. I'd like to talk about the quantum theory of diamagnetism. Here, mu 0 is the permeability of free space, n is the number of particles or number of atoms per unit volume, z is the atomic number of the atom, E is the charge of electron, and m is the mass of electron. Okay, R square is the mean square distance from the electron to the nucleus. Okay, here the negative sign indicates that this susceptibility is diamagnetic. Okay, so in the next video I'll be talking about the quantum mechanical theory of diamagnetism or quantum mechanical description of diamagnetism. Okay.